Hello everyone, I am Arda Egünlü and I will be presenting PAIR, Phone as an Augmented Immersive Reality Controller. We did this work at the University of British Columbia with Robert Xiao. So immersive head-mounted augmented reality allows users to overlay 3D digital content on their own view of the world. Current generation devices primarily support interactions through gesture, gaze, and voice, which are readily available, but mostly lack precision and tactility, rendering them fatiguing for extended interactions. We also have controllers like the HoloLens's clicker, but these devices are also not very expressive. So we propose using smartphones, which are also readily available as companion devices complementing existing AR interaction modalities. We leverage user familiarity with the smartphone interactions coupled with support for precise tactile touch input to unlock a broad range of interaction techniques and applications. For example, here you see an AR rendered sword or a bow overlaid on the phone. We have some other applications that you will see in a second. And also smartphones have been previously proposed as companions to AR headsets as controllers. Notably, most of these past systems, though, have employed external tracking systems to obtain the sixth-of position of the phone, spatial position. So our goal with PAIR was to explicitly demonstrate the feasibility of using an off-the-shelf phone together with an off-the-shelf unmodified headset. So in terms of implementation, in order to use the phone as a six-stop controller, the phone and the headset needs to be tracked within a uniform coordinate system. We accomplish this by having the phone and the headset track themselves in their own coordinate systems, first of all, and then we align these coordinate systems by displaying these grids of markers around the bezel of the phone, and then detecting them with the headset's front camera. This provides the phone's six-stop position in the coordinate system of the headset, and at startup time, this initial detection of the grid can provide the initial alignment. Also, by using a bezel of markers, we gain some amount of occlusion resilience. Here you see some of the bezel configurations that we have used for different applications. Well, if the visual inertial odometry that we use to track the phone was perfect, the markers wouldn't be needed after the initial alignment. However, the phone's own tracking is error-prone and susceptible to drift over time, especially after rapid movements or as the phone moves into unexplored places within the environment. For this reason, PAIR doesn't rely on this initial alignment alone, but continuously scans for markers. And whenever markers become visible, we realign. This ensures consistent and healthy tracking. Yes, what kind of interactions do we enable? The phone can be an input device and an output device. The output device is obvious. We have a display, tactile feedback, audio output, and also now we have enabled six-stop input and touchscreen input. And there are curious ways to combine these six-stop and touchscreen input. We provide two novelties that we named the three-dimensional trackpad and catapult swipe. Yes, this is a room-level Fruit Ninja application. So here you see the six-stop tracking is stable and fast enough to enable a room-level Fruit Ninja application like this. Yes, here the user is browsing a catalog of furniture and the furnitures are popping up on top of the phone. And now by using the familiar touchscreen interactions like panning the finger, zooming in, rotating with two fingers, or using a color palette, the user can customize this furniture. And what is this? This is our three-dimensional virtual trackpad. And unlike a regular trackpad that tracks a finger on a fixed 2D surface, here the phone's orientation determines the plane of motion. So that plane of motion you see as that gray plane, and the user pans the finger to move that cube in a three-dimensional volume. Here, the position and orientation of the phone together with swipes, can be used to initialize objects into the AR world. Yes, swiping dollar bills into existence. Yes, you see the user kneeling on the floor. There's a quiver there with explosive arrows. You pick them up. And evaluation. We tested the 3D positional accuracy of our tracking approach in a Vicon-equipped motion tracking lab. And what did we do? We recorded 35 different gestures and activities. Activities like idling, walking and looking around. And gestures are stuff like vertical swipes, in and out swipes, horizontal swipes, under different variations. Marker variations correspond to different marker bezels that you have seen on the previous slides, like a full bezel of markers, just the left column, just the top row, stuff like that. Speed is either fast or slow, and orientation corresponds to whether for example, for horizontal swipes, is whether the phone is facing upwards, leftwards, rightwards, and so on. So let's take a step back and think about what kind of errors we have, or what are the sources of error we have. HoloLens tracks itself, which is error prone. The phone tracks itself, in our case through ARKit, error prone. And then we display markers on the phone and detect them. We use Aruko, error prone. So 3 sources of error. In our approach, we correct for the phone's own tracking by using the Aruko detection. We could have used the perfect system for that instead of Aruko, like as close to perfect as possible, like Vicon. That we named the baseline optimal ARKit error, in which we correct ARKit errors with Vicon reported phone positions. In 2, the ARKit only error, we only correct the initial alignment using Vicon, and then do not correct at all after that. So the error accumulates. In the 3rd one, the final error, this is our systems error. We correct the ARKit error using Aruko tags, Aruko corrected positions. So here we see that final errors, our errors, are significantly lower than ARKit only errors, which is good news. And we also found the speed to be significant, which implies that faster motions are producing more error, suggesting latency plays a part here. Also, marker position orientation were not found to be significant, implying different configurations can be used confidently for a healthy tracking experience. Yes. In terms of limitations, we have some 150 milliseconds of latency. This comes through with a combination of ARKit, networking, marker detection, all contributing to it. These all happen in parallel, but still add up. Sometimes this produces visible lag. In terms of drift, rapid motions produce motion blur on camera, which comes into play in monocular SLAM, making it fall back into just inertial odometry. And future work for mitigation of drift and latency, different approaches can be taken. New LiDAR-enabled phones can be used. A more optimized tracker algorithm can be used. Communication delays can be reduced by using something like BLE rather than Wi-Fi. Also, just different types of synchronization can be used by using the historical head position rather than the most current one that we use in our approach. And in conclusion, we demonstrate the viability of an off-the-shelf smartphone as a 6-stop controller for AR, and the versatility and expressiveness of familiar smartphone interactions in this context. Yes, thank you for listening.